What makes right angles and circles combine? Anything that swings on a hinge, of which there are a number of things that swing on hinges. But before I get into that, I want to review two things, one of which we talked about last week. Do you remember how I showed you that you can project the measurements around a cylinder by taking that and turning that into a circle? You remember that? You know that you don't have to do the whole circle. You only need to do what? Half of the circle. If you're only doing the front part of this, right? If you're only doing the front part of that cylinder, you can make your divisions and just go like that down there from that. You don't need to do the back unless you're doing through the back. That can help simplify things a bit perhaps, but one thing, when you're making the divisions on the clock face, for example, and you've got something that's looking, actually, I just did that, violating that rule of placing the ellipse that I had taught you about so carefully a few weeks ago. When you're making that division on that clock face there, you can do it without doing a full circle. You need to divide this thing up, project it out, and if you just do half a circle, you can project those back and then run that line off to that vanishing point, and you'll get them for both sides. And that simplifies it a bit. It won't work if these divisions are not even. If you're making it so that these are getting further apart, then you have to go around the whole circle, but if it's symmetrical left to right, you can just run this line, then throw the line back to the vanishing point, and you'll find the hidden parts. The reason I did it with a full circle last week is I wanted you to get the whole picture of it before you go for the shortcuts. But now I want to review something from about 6 nights ago that will apply to this business of things swinging. It may not seem like it will at first, but it's very basic. This is a horizon line. In 1-point perspective, if you've got a box somewhere here, the lines will be either vertical, horizontal, or they will converge back to that vanishing point. If you have a box in 2-point perspective that is sitting level on the ground, right here, it can be the same box, and we'll place vanishing points at these. Actually, better tighten those up a bit. You will still have vanishing points that will converge at that horizon line. That is, this is level with that. All we've done is spun. This isn't really a square. It would have to be trimmed significantly to be a square and extend a bit. But if we spin a box, we have vertical lines, and now instead of horizontal lines, lines that go to the right and lines that go to the left. But it's level ground. And so the horizon line stays consistent. Now I'll show you how that's important when you have to draw a door opening. 1-point perspective to keep this simple. But first of all, before we draw a door opening, we'll say that this is the wall, and the door will be right there. Let's get in a helicopter and look straight down on that wall. And we're going to see that the door might take up that amount of space right there. There'll be a door knob right about there. There'll be a hinge somewhere there. Now, what's going to happen if that door opens? What shape will this right angle thing make? It will make a perfect circle. What is the definition of a circle? Somebody said a closed symmetrical curve. That's pretty good. An ellipse is a closed symmetrical curve, but an ellipse or a circle is a closed symmetrical curve that's symmetrical any way you slice it through the middle. But there's another definition of a circle that helps us here. A circle is a line that stays in constant relation to a point. So if we've got a point, we have a line, and it's changing relationship to that. But if it stays in constant distance relationship, that it's always that far away from that point, it will make a circle. And that's what happens when you open a door. This becomes the pivot, and the circle will always be exactly like that, all the way around. You can just kind of connect the dots around this pivot point. Now, when you tip a circle into perspective, it becomes an ellipse. So that means when you're doing this door that we'll say is at eye level, let's make it more like the proportion of a real door, put the knob right there. We'll say eye level is about there, even though you don't see the horizon. Now, the next picture in your storyboard is the door opening, and you go, "Ah!" What do you do next? You've got to track how that thing opens, which will be an ellipse down there somewhere. How open? You choose how open. The more open it is, the more wide angle effect you'll get. But we know, since this is our eye level, and if we're going to think of this thing as a great big cylinder, we know that this will curve up, that will curve a little. This would be a straight line if this was a great big cylinder, right? The middle of a cylinder. And this is going to curve down like that, right? Don't worry about this one. You could figure it out. You could eyeball it. But let's not worry about it for now. Let's worry about the fact that that's the center of the circle right there. The ellipse will be constructed, as we remember from last week, with the major axis a little front of it. And let's just choose to make it so that the arc of that ellipse is something like that. Now, what you've got to do, you open that door and you decide where on that track am I opening it to, and you draw a line from there to where you're opening it to, and you stop. Now, where would I go? Vertical. It's going to, where do I stop though? Let me show you where to stop. Take this line that you found and run it back to the horizon line. And now where will you go? Remember, this line and that one that we're looking for, that is this and this, are parallel lines. They aren't tipping, so if you ran a line from there to there, it's going to intersect right there, and that's where it's going to be. Did that make sense? Because the same thing is happening with the door with this, as with this. Let's open the door further. Let's open it so it goes all the way out like that, right? The doorknob is right here. Let's make it so that the doorknob is going to be hidden. Open it so that it's going like so. It hits that point on the ellipse. Where do I go now? Vertical, but where do I stop? Well, this is now going off to our right, so I should find a point there and then run a point from there to there, and it will connect there, and that will and then you'll have that doorknob over on the other side. But of course, a door is not made out of a thin strip of plastic. It's got this thickness to it, so we have another plane to deal with, do we not? Which means there's going to be some thickness here. For simplicity's sake, I'm going to put it over like so. Where is that going to go? You will eyeball it. That's good enough for now. You will eyeball it, and it's got to hit that horizon line somewhere, right? And if it hits it over there, this plane is going to be parallel to it, and you'll see you've got a three-dimensional solid core door going on there, right? Because this plane of the edge of the door is simply this now. This plane is this plane of the door. It's level. It stays level no matter how many times you swing it around, which means all that happens is that these vanishing points crawl along the horizon line. If you put that so that it spins, it crawls along the horizon line, eventually comes back into one point. This would go back into one point at which place? If you opened it so that the edge was facing right there, you'd have that door back in one point. And that's where it might help to know where that arc is right there. Does that make sense? You've got a door made out of right angles, but it's on a pivot which makes perfect circles, which this is where all this about putting circles in space becomes handy. But that's one point perspective.
So if you wanted to make that door look vanishing points in closer?
You would do that, and that would make this part look like it was coming closer to you, right? That would make this plane more like that, right? Which would be great. But if you want it so that you've got a wide angle lens effect happening, not just on the corners, but on the whole door, then you'd open up this ellipse down here and open up that ellipse down there, and you'd even curve these parts of the door like that. Because that's what happens when you look at a wide angle lens and have a door go like that. It bends. You'd still have to decide where your horizon line was. You'd still have to open up this ellipse more than that one if your horizon line, if your eye level is closer to the top. But you'd exaggerate those. Also, if you've got a door across the street and you're looking at it through a telescope, that's going to be a real thin ellipse down there. So that is the way you would do that. Choosing that ellipse was intuitive. There's a way to measure it. And I'm going to show you that in 3 to 4 weeks when we get to the projecting plans, which is a bit tough, and it might help you to understand this lecture, but I'm trying to take this with some kind of one thing at a time, and so I haven't done plan projection yet. But now I want to show you, that was in one point. One ellipse, the minor axis was right there on the vertical part. Let's do something a little more complicated and make the same point, that we've got a box, a cardboard box with one lid. It could be any of 4 flaps on that cardboard box, but let's just say one to keep it simple. And let's do a diagram of this cardboard box. So that we're not, so we'll make it a little more complicated by, instead of making it a square box, we'll make it a vertical box. And that's the side view. And the hinge will be like this. Which means that if you open that, that will make a perfect circle. And a perfect circle fits into a what? A perfect square. So let's square this up so that we understand what's going on here without any doubt. There's our square, there's our box flap, and there's the perfect circle in there. Now, remember how you find the center of any rectangle or square, but how would we find the center quickly? If you run a line from here to here, it's got to intersect that middle point. So that's how we can kind of test that. Now let's put it in perspective, in 2-point perspective. Try to make it pretty similar to those proportions by eyeballing. Again, I can make this perfect if I take the time to do a plan projection, which you'll learn 4 weeks from tonight. But I'm eyeballing it so that I don't spend a great deal of time just getting the drawing up there. We know that the lid is going to flip up from this hinge right here, right? So we've got to solve that problem. And it's going to make a perfect circle in perspective, which will be an ellipse. A perfect circle fits into a perfect square. Do you see how if we could just find this square, if we could find that on there, we'd know how to fit a perfect ellipse in it, and we'd be able to track the movement of that lid. Say we want to open it at something like that or whatever. Okay, here's how we can find it. Tough to measure that one back so far. We haven't learned how, because we know it's going to get smaller as it goes back. But it isn't tough to measure one of these vertical lines because they aren't foreshortened, are they? So we have to be able to see what a square looks like in perspective enough to know how to divide that up. and that comes with practice, unless you do a plan projection. I'm going to do it by eyeball. Let's say that is a square. Now double that. Make sure it's exactly double. Now, do you see what I just did? Go from that point where we need to go off to a vanishing point somewhere here, which means our eye level. I've sort of arbitrarily placed these vanishing points. Throw that off to there. Now, how will I find? What I'm looking for is this line, right? I'm trying to do a big square. I'm looking for this line. How will I find it? Remember this? Woo! Run a line from there through the middle, and you see that it will intersect at that point, which will be a square. Now, I can tell by looking at it I blew it. You know why? This side is more wide-angle lensed than this side. Right, I've got that vanishing point in too close. So I'm going to, I've showed you the theory of how to do it. If I was doing this with a T-square, I'd be able to get it more accurate. But I'm going to fix it by eyeball, so that it's something like so. Okay, now, what have I got to place in there? An ellipse. Right angle will go, the minor axis will point where? Like an axle off to that vanishing point. If you can get that in there, then you'll know there's going to be an ellipse that will fit just like so. And do you see what I found? I found the invisible tracking line to know that if I open up that lid that high, it'll go right there. If I open it up this high, it'll go right there. And if I open it up that high, do you see the idea? But now where do I go? I've got to find the line that goes off to that point. So I can run it like so, run it like so, run it like so. But now what do I do? I've got to find this line over here. Two ways to do it. The first way is the tough way. The easier way, I'll teach you next week. I'm going to show you the tough way so that you understand what you're looking at, because the problem that I'm going to teach you next week is inclined planes and vanishing traces. I'm going to give you a hint at the solution tonight, but I'm going to develop it next week in some detail. One way you can do this is simply project this square, this box over here, right? You're still going to have to find your vanishing points, draw through there, and then just do the other ellipse on the other plane, which will be a more open ellipse over there. It will be more open than this one because it's further away. It ought to be about like so. And if you can do that, you see that it's going to intersect right there, and you'll find that hidden line by connecting the dots. Right? You'll find it over here by connecting the dots. Now, I know how complicated that gets to look. I mean, there's something kind of romantic about all those lines, too. It's kind of nice for its own sake, but it's not what you're doing it for. You're doing it to find hidden lines. So simpler is better. And here's what you will see next week. I want to darken up these lines, or lighten up these lines, as the case may be, that make the open box. You see, there's that lid. Oops, got to make sure it's pointing back to that pivot. There's that lid, and you can make it go down there and down there, and it's going to go off to that. And you wouldn't even need to find the hidden plane for the other side. You get the idea? Made up entirely of right angles, but because it pivots in a perfect circle, a perfect ellipse is going to help you find the hidden parts. But here's the thing we'll talk about next week that will simplify how you find some of those hidden lines. There's something called the vanishing trace. What is that? Can you imagine taking this drawing and going like this? And what will happen? This thing which is spinning is going to start spinning the way this is spinning. or the way that door was spinning. Which, in other words, let me show it to you this way if I can. Here we've got a box flap going like that, right? And you're trying to find where are these lines converging. They're no longer level. You can make it level by going like this. There, do you see now? It's just a door on a hinge and it's staying level, which means there's going to be a line like that, and these are going to converge at vanishing points, always on that same line, because it's level, spinning on a vertical line, right? But when you put it like this, now you're going to have two kinds of line. This becomes the vanishing line, and this becomes the vanishing trace, which will be at right angles to it. Now, I know I went over that quickly. The idea is, as I told you a few weeks ago, you can simplify a lot of problems. You can solve a lot of perspective problems if you just remember to go 90 degrees and see what happens. And next week, this business of the vanishing trace, I'm going to talk a lot about that. So that you bring this complicated two-point perspective problem, flip it, and you come right back to the same problem of opening that door where the lines, vanishing points, crawl along a horizon line. Any question about this? Here is the big trick. The big trick is knowing squares, not just right angles as they apply to squares, knowing squares and circles. And when you've mastered squares and circles, the big trick is knowing cubes, not just boxes, cubes and cylinders and spheres. You see, you have to know squares and circles and how they look in perspective. Then you got to make them 3D, which they become cubes and cylinders and spheres. Knowing them by eye. And when you do, and you understand the principles involved, I mean, some people have really never thought about the fact that a hinge is the middle of a circle. When you get these principles, then you can start applying this to all sorts of problems. But the trick is to understand the principles that apply to squares and circles. If you see me do this, then you say, okay, good. Now I know how to do a box flap on a box shaped like that or a square box. But then when you come to the problem of a box that is shaped like this, and the flap only goes halfway, or let's say the flap goes the whole way, and you say, gee, I don't know how to do that. I only learned how to do it with these kinds of boxes. Then you haven't grasped the principle. The principle is squares and circles are the simplest things you can reduce these to, so you have to find a way to make this into a square in space, and then double that, measuring it out, and then making it go out, doubling it, finding that line through there, getting a great big square, finding the ellipse for that. And that way you know you're getting the principle. And you can apply this to all sorts of problems, including human limbs. People that draw the figure, you've heard some people say that you don't need perspective to draw the figure. But this elbow is a pivot for something that makes an arc that is about a quarter or a third of a perfect circle. Which, when you're going like that, you see that. But if I'm going like this and throwing something towards you, it's making a foreshortened ellipse. And the more foreshortened, the more important it is to know. How do you know how foreshortened? If you know circles in space, it means that you can animate people dancing and twirling around and know there's a point for this point and there's a point for here, that little bump on the little finger side, which is the end of the ulna. And if you can place that point and that point in any position, you're well on your way to solving the problem of the lower arm. If you know this point, actually it's about an inch into there, that point and this point, and you can do the same thing and know that if they swing in a circle or a portion of a circle, how to find that, you can do figures dancing.